Okay, good afternoon everyone. Good afternoon. Good afternoon. Thank you for coming. Your exam is open on carbon. Okay, we will not discuss it until Wednesday, but good luck to you. Try your best. Okay. All right. We were looking at electrical systems. I want to keep this lecture very quick and brief. Okay. And as I have mentioned, since you've come across electrical system elements in the past in your circuits class, I will not be going into the physical details of all of these elements. I won't be going into looking at how a capacitor is, achieved, or how the capacitance of the capacitor is achieved, and so on. Okay, or the construction of an actual physical capacitor. We are going to use them as placeholders to develop a system dynamics point of view. Okay, that's where my interests are, and our interests are in this class. It's very limited, of course, in scope, but this is sufficient to move on to the next step. Okay. All right. So with that said, very brief recap of a resistor element. We started off with that last class. So this is the current, voltage, relations for passive elements. And what is our aim? Our aim is, in electrical systems, we can model electrical systems by a combination of the passive elements in conjunction with some kind of a source, okay, some source of energy. And we can achieve whatever we want to achieve with that combination. Okay? That's our motive in doing these things. So resistor element is the first passive element. We had the voltage difference. Let's call this VA, VB, plus or minus. This is a passive element, so the passive sign convention. I of t, the current comes from the source and passes through the terminal with a higher potential, and then passes out through the terminal with a lower potential. The potential difference VR is VA minus VB. This is typically called a potential drop, because you see that the current is flowing from the plus to the negative terminal, so there is a drop in the potential as the current flows through the element. And quite simply, Ohm's law gives us that VR of t is R times I of t. R is a resistance, which is a function of the resistivity of the material. It's the characterization of the capability of a material to resist the flow of current through it. Okay? This is a material property, like Young's modulus is a material property. Poisson's ratio is a material property. This is a material property. Resistivity is a material property. Resistance comes from that. This is in a time domain. In the frequency domain, which is where we want to go, because the next lecture, which is Wednesday when hopefully all of us are here, it's a very, very important lecture, because we will be exposing ourselves to handling harmonic inputs in the frequency domain. Okay? So to do that, we have to take the Laplace transform on both sides and define the impedance of a resistor. So VR of S is R times I of S. So this is in the Laplace domain. The impedance is defined as ZR. Is VR okay, this is the electrical impedance. Of the resistor. Okay, this is where we stop. And I will do a very similar quick treatment of capacitors and inductors as well. The second element that we will use to model circuits or electrical systems is a capacitor element. Capacitors, they are used to model the capability of electrical systems to store electric energy in their electric field. Electric field is electric force per charge. Okay? So capacitors typically store charges. Okay? So they store charges, which is equivalent to storing electrical energy within the electric field. And capacitors, as I mentioned last class, I could have a fully charged capacitor, place it in a circuit. That capacitor could act as a source element. Okay, it could actually light up a bulb for me, depending on the amount of charge it has. But we will not be using capacitors that way. For us, capacitors are always fully discharged when we start the circuit. So they will always be passive elements for us, not sources of energy, not sources of electrical energy. Okay? And for a capacitor, the charge stored is proportional to the voltage drop across the capacitor element. This is a capacitor element I'm drawing. Plus, minus, terminal A, terminal B, and VC is the difference between the two. I mean, of course, different figures, so I can use the same alphabets. And this is I of t. And the charge stored on the plates of the capacitor, as you can see, those two vertical lines, they represent the plates of the capacitor. The charge is stored between the plates. And in between the plates, you could have either vacuum or you could have a dielectric medium, like air. Air is completely fine, you could have that. We are not interested in these details, as I mentioned. Okay? It's not my intention. So here, charge is proportional to the voltage drop across the capacitor. Okay? Or Q of t is C times Vc of t, where C is the capacitance of the capacitor. Capacitance is measured in farads, as you know. Named after Michael Faraday. And 1 farad is 1 coulomb per volt. So you see Q is charge measured in coulomb. Volt, as you know, is joules per coulomb. All right. And what we will do is, okay, we will say that there is a relationship between current and charge. You see, I don't want the relationship between charge and voltage. I want current and voltage characteristics. So we bring upon, recall, current is charge in motion. So this is dq by dt. And so if I just make some brute force substitutions, instead of Q of t, I bring in C times Vc. Then I have I of t, d by dt. C is the constant of proportionality, so it does not get differentiated. So I have I of t is C So this is the current voltage relationship for capacitor elements. Okay? And of course you can integrate it on both sides. If you do the integration on both sides, integral of I dt is C times d integral of dv, and so I have Vc of t Okay, I just perform the integration. Vc of 0 is always 0 for us because we start off with an empty capacitor. Okay, we don't look at the discharge of the capacitor, we look at the charging of the capacitor. So this is always 0 for us. And so we have Vc 1 by C, C is the capacitance, and integral I dt. It's a generic expression, okay, going from 0 to t. Obviously I should have an integration dummy within, but I'm not going to do that, and this is equivalent to I of t is C this is in the time domain. Okay. Then we take the Laplace transform on both sides. For that I'm going to choose this guy, this expression here. Take the Laplace transform on both sides, we will be able to define the impedance of the capacitor. So I of t, Laplace is Laplace of C dvc by dt. Laplace of the differential is s times the Laplace of the function itself. So this is C times s times the Laplace variable there. Okay, and so we have I of s is Cs Vc of s, and I can define now the impedance of the capacitor as Zc of s is Vc, which is okay. These are expressions that I hope you have come across. I'm sure you've come across in electrical systems. Am I right in assuming that? Or okay. So this is actually a refresher for many of you, most of you, all of you. Alright, this is the impedance of a capacitor element. We will be remembering this creature and using it in many of our problems. Okay, we will go to the next element, which is the inductor. Okay, I'm going to pull this board down. Inductor. What is an inductor? All right, my gentlemen friends there. What is an inductor?
Inductor?
Yes.
It's I'm not sure.
Good for you. So an inductor is actually a coiled current carrying conductor. Okay. Coiled current carrying conductor. Which means if you look at your electric bulb, light bulb, you will see a filament bulb, of course, not the LED ones. You look at a filament bulb, you'll see a filament with a coil there. That is actually an inductor. And the beauty of this thing is, from Ampere's law, if I have current flowing through a coiled conductor, it creates a magnetic field. And the magnetic flux of this field, which is a measure of the distribution of the magnetic field, is proportional to the current flowing through that creature. Okay? So this is all Ampere's law. A current I of t flowing through an inductor generates a magnetic field. Right? Same idea, if I have current flowing through a capacitor, it generates an electric field and electrical energy can be stored in this electric field. Current flowing through an inductor generates a magnetic field. Energy can be stored within this magnetic field and of course can be used for potential purposes, our own selfish needs. Alright, so here is a representation of an inductor. Looks like a torsional spring. One of my most favorite elements is a torsional spring. It always causes confusion, okay, which is why I like it. Alright, so here is a representation of an inductor. Okay, I have the voltages across the terminals. VA, VB, VL of t is the voltage drop across the inductor element and it's VA minus VB as you know. I of t is the current flowing through this inductor and here is what happens. Okay, so this current generates a magnetic field. The magnetic flux of that field, which is going to be called as phi, is proportional to the current flowing through it, and the current flowing through it is I of t, and the constant of proportionality is called capital L, where L is called the self-inductance or simply the inductance of the coil. Or just inductance for us. This is different from mutual inductance. I'm not going to go into the details of those things. It's not relevant to us, but make the distinction in your mind. Okay, so this is typically Ampere's law, and then Faraday's law says the following. The magnitude of the rate of change of the magnetic flux is equal to the voltage drop across the inductor. So magnitude of and so obviously you know what we're going to do. We're going to substitute for phi. Right? This is phi of t. And so if I do the substitution for phi, d phi by dt is L di by dt. So substitute. Which tells me that this is the current voltage relationship in the time domain for an inductor. These are all things we have to remember. Of course, you'll have a formula sheet and it's also open book, open notes and all those things. But it still behooves to understand this and maybe memorize these things. Very critical things, right? You want to use them very quickly. Laplace domain. Switch off all initial conditions. Laplace of VL of t is VL of S. And L times Laplace of di by dt is S times I of S. And so I can define the impedance of the inductor as ZL is equal to VL I, and this is LS. As you see, this is a sort of a transfer function, right? I have the current entering, and then there is a potential drop, and the relationship between the potential drop and the current through that element is an electrical impedance quantity. Why are we using these impedance fellows? It's because we are going to go to the frequency domain. We are going to do that on Wednesday. Frequency domain is much more confusing than time domain. Okay? and we want to take it step by step. And the impedance blocks are the best way to actually model things in the frequency domain, because you directly get the transfer function. Once you get the transfer function, you just do some substitutions and you call it a day. Okay, some more review. Once again, you've seen these before. The foundational laws that govern electrical systems, two of them. Kirchhoff's current law, Kirchhoff's voltage law. Okay, once again, very basic stuff. So laws to help obtain system models. What was the law we used in mechanical systems? Newton's law, right? Good old Newton. You have the equivalent of that creature in electrical systems, that's Kirchhoff. And Kirchhoff has two laws. One is a statement of conservation of mass, which is the Kirchhoff's current law. The other is a statement of conservation of energy, which is the voltage law. Conservation of mass, conservation of energy is nothing new. You've done this in thermodynamics for a living so far. Okay, so this is exactly the restatement of these things for electrical systems. Okay, so first thing, Kirchhoff's. Please notice the spelling and please do not butcher it. Kirchhoff's current law essentially says that the algebraic sum of the currents at a node is 0. Okay, so the sum of currents at a node is 0, which tells you that there is no loss of charge in an electrical circuit, which means that all the charges are conserved, which is the same as the conservation of mass, because we said that when you do the analogy between fluid systems and electrical systems, quantity of fluid, the mass of the fluid is equivalent to the charge, right? So that's the analogy that we're making use of. So this is analogous to conservation of mass or charge quick things. And if you go to electrical systems, they will assign a sign convention. Current entering the node is positive, current leaving the node is negative, and so on and so forth. I don't want to do those things. Take a node. Kirchhoff's current law essentially says that all the currents entering the node should be equal to all the currents leaving the node. Okay, so this is some I1, I2, I3, I4. KCL says sum of all the currents entering the node is equal to the sum of all the currents leaving the node. And you can do this for each and every node within each and every loop of an entire circuit. Okay? And if I apply this here, I1 plus I2 simple, very nice, very effective. That's it for the Kirchhoff's current law, and then Kirchhoff's voltage law is KVL. Once again, this is not new stuff, I believe. And this quite simply says the following. The algebraic sum of all the voltages across all the elements in any closed loop path of a circuit is 0. Okay? So the algebraic sum of all voltages across all elements in any closed loop path of a circuit is 0. And this is the thing with the restatement of conservation of energy, right? So energy can either be created or destroyed, it can only be converted from one form to the other. And same idea here, if I have potential drops across the passive elements, it will be equal to the potential rises across the source elements. That's what this law says. And I'm going to write that next statement down. But before that, I would like to pull down the panel. We will take one simple, silly example and execute that. So the sum of potential drops across all passive elements this is equal to the, and this law is a restatement of this fact, essentially, is equal to the sum of potential arises across all sources. Take a simple example, okay? Now that I'm going to take one of the nodes arbitrarily and ground it. Does not matter which. I have two load elements, I'm going to call them as L1 and L2. Okay? And then I have one source element which you see drawn in this circle. So this is a voltage source. I'm going to call it as a source element. And let me assign the signs for these things. Plus, minus, plus, minus, plus, minus. So I have the current flowing in a closed loop, clockwise sense. And each of these nodes, I'm going to call them by some names, okay? VA, VB, VC, VD. So VA, VB, voltage here, V suffix C, V suffix D. Okay, these are all the voltages at each of those terminals, okay? Voltage drop across the load element, L1 is V1. Is VA minus VB. Across L2 is VB minus VC. V2 is VB minus VC. Okay, I need to write them all in small letters. Sorry about that. This is all small or lowercase voltages in time domain. So VA, VB, C, VD, and then the voltage across the source element is VA minus V suffix D. Vs is VA minus V suffix D. Can somebody tell me the voltage at Vc? What is Vc equal to? It has to be 0. What's V suffix D equal to? Has to be 0 as well, because there's no element between C and D, right? So you know this. This is ground, and that is the consequence of having no elements there. Apply Kirchhoff's voltage law. Once again, simple illustrations. You've applied this multiple times to maybe more complicated problems. Here is how I do it. Select any node. Let's say I select node VC. Write down the voltage at that node. Travel to the next node. Subtract that voltage from the previous node. Okay, so VC minus V suffix D. Then I go to V suffix D. I subtract the voltage, and what direction do I travel? Does not matter. Travel clockwise, travel counterclockwise, head over heels, who cares? V suffix D minus V suffix A. I am traveling clockwise. You will get the same result if you travel counterclockwise, and I have showed it in my lecture notes, which I'll post after class. Then I go to VA, subtract the voltage of the next node from that node, and then VB minus VC. What should this equal to? Should equal to 0, right? And does it work out? There is V suffix C minus V suffix C cancels off. V suffix D minus plus V suffix D cancels off. V suffix A minus plus V suffix A cancels off. Minus VB plus VB cancels off. So I get 0 is equal to 0, or QED, right? So this is equal to 0. So this is beautiful. Works out. But does not tell me anything new. So what do? Think. VC is 0, VD is 0, so get rid of this guy. V suffix D minus V suffix A is the negative of Vs. So I write this as minus Vs, it's a function of time, let's say. V suffix A minus V suffix B is nothing but our good friend V1, which is the voltage drop across the load element. So plus, this is V1, and obviously V suffix B minus V suffix C is V2. So this is plus. Or you essentially see that the potential rise across the source is equal to the potential drop across the load elements, the sum of the potential drops. And does not matter which direction you take, okay? You can go clockwise, counterclockwise, you'll get the same result. This always holds true, no matter who you are, okay? Alright, now comes the last part of what I'm planning to do for today's lecture. This is all fantastic, nothing new, not useful as well for me, because my aim is this. My aim is obtain the system ordinary differential equation or obtain the system transfer function. Right? Because if I get that, then I can perform analysis, and I'm mostly interested in the analysis. I'm not interested in obtaining differential equations that anybody can do. To achieve the differential equations quickly, we use the impedance blocks. Okay? So use impedances. To obtain system ODE, and this Kirchhoff's current law, Kirchhoff's voltage law, these are fundamental laws. They should work whether you're in the time domain or whether you're in the frequency domain. Should not distinguish between the two. Okay? And to do this quickly, I'm going to draw two boxes, connect them in series, and come up with a very quick way of figuring out, okay, how do I combine these two together? And you probably would have done this. So impedances in series. I take two impedance blocks. They could be the impedance of a resistor, it could be the impedance of a capacitor combined, connected together, so that's an RC circuit, which is my next stop, right, which is a low pass filter, which we're going to get into, right. So I just call them as Z1 and Z2, okay, so this is Z1 of S. Z2 of S. If I have some current flowing through them, you obviously see that the same current has to flow through. Okay? So I have the same current flowing through two impedances in series. So impedances are said to be in series if they have the same current flowing through. So they have the same current flowing through them. Some people in this room want to use this panel here, so they are stealing all the chalks, but they don't know who they're playing with. All right. I have voltage drops across these impedance elements designed now. I'm going to call them as V1 and V2. Okay, I'm just going to call them as V1 of S and V2 of S, and all we're going to do is this. If I have an impedance, what's an impedance? Voltage by current. So what's Z1 by definition? Okay, and then what's Z2 is the current flowing through it. I have the voltage across that element. So Z2 is this is a lot of work, right? So what we say is, okay, if I see these two creatures in series, or if I see a set of them in series, scrunch them together into one and call it as an effective impedance. So this is going to be now replaced by an effective impedance called Z effective. Or Z equivalent. Okay, so this is Z equivalent. The voltage drop across this is nothing but the sum of the voltage drops across the two elements. Okay, so this is now going to be V1 of S. Call it as V of S is, and this is I of S. And obviously you can see that Z equivalent is V of S by I of S. Right. So what am I going to do? I'm going to take that V of S and say V equivalent of S is replace it with V1 plus V2, and you obviously know where I'm going with this, because instead of V1 I'm going to substitute Z1 times I, instead of V2 I'm going to substitute Z2 times I. So this is Z1 V2 by I of S. I of S is a common factor, cancels out, and so I have Z equivalent in series is Z1 plus Z2. If you have n impedances in series, this is just the sum of all of those things. Okay, so Zn or I is equal to 1 to n. Okay, so this is the impedances in series. Once again, if I'm not mistaken, have you come across all of these things? Okay, it's good to see things multiple times. Okay, memory is a fickle creature. And I'm not going to derive the next one, but I could have impedances in parallel as well. And they will follow the reciprocal rule, right? Similar to what? Similar to? Yes?
Resistance in parallel.
Resistance in parallel.
Combines like impedance in parallel.
How about springs? What do they do? If I have springs in series, what do they do? It's the opposite. Springs in parallel add up, springs in series obey the reciprocal rule. Okay? So remember, resistors and impedances, they behave the same way. Resistor is the complete antithesis of a spring, though they look the same. Because resistors dissipate, springs store. So physically and figuratively, they are the antithesis. Alright? Alright, let's not dwell on that. So, second thing, impedance in parallel. Just a small note. If I have impedances in parallel, they have the same voltage drop across them. The same. Can everybody see my writing clearly? People in the back? Fantastic. Alright, I'll just draw it and then we will say we know how to get this. Okay, so I have current I of S entering, sees a node. When a current sees a node, bifurcates into two, moves out. And at that particular node, I can apply Kirchhoff's current law and say that I of S is I1 plus I2. KCL. Then those two blocks, I'll call them as Z1 and Z2. Z1 of S and Z2 of S. Same voltage drop across these creatures. This can be replaced by an equivalent impedance. V of S, and if I go ahead and write the result here, Z equivalent in parallel, 1 by Z equivalent by Z equivalent in parallel. Zn or 1 by Zi. Okay, so these two things are things that we're going to remember. There are only a few things we need to remember in electrical circuits. The impedances of the individual elements. Impedance of resistor is R, capacitor is 1 by Cs, and Ls for an inductor. Remember these two. Remember Kirchhoff's laws. You're good to go. Where are we going to go with this? Next class. I'm going to start frequency response analysis. My impression is you've come across this as well, in the form of Bode plots, right? Or no? Come across that too, okay? So we will go over the basic ideas of why frequency response analysis works, why do we say S is equal to j omega, and what exactly is the beautiful idea behind it. It's a Fourier series, right? Superposition and so on. So we will start with that, and I will very quickly go to first and second order Bode plots. And a couple of questions that we want to answer. Why is the Bode plot in a log scale? Why do you have that factor of 20, that pesky fellow sitting next to the Bode plots? Okay, there are a couple of things that I want to answer. And maybe you've come across this as well. Maybe you've done everything before, but bear with me, we will get through it again. Good luck.